Last time we derived the formula for the area of a surface of revolution. For example, if we have an arc and we rotate this arc about this x-axis, we get a surface of revolution. And to find this surface area, we found that is going to be the integral. If we want about this x-axis, then will be 2 pi y. Well, think about that as the circumference of the circle by taking a point on the curve and rotate about this x-axis, then you get a circle. The circumference of this circle is 2 pi times this r. R here is y. So 2 pi y, that's the circumference of this circle. And then ds. ds here is the differential arc length. Think about that as a small increment of arc. So for the ds here, you have two different ways to represent that, either this way or this way. Depends on the equation of x and y. So sometimes dy dx is easy to find, sometimes dx dy is easy to find, and then you can decide which one to use. And sometimes you can use both. Okay, now this is when the curve is revolved about this x-axis. Now over here, if this arc over here is revolved about this y-axis, you also get a surface of revolution. And then this time, when you take a point on this arc and rotate about this y-axis, then the circumference of this circle is going to be 2 pi x. X here is the radius of this circle. And then the ds here, the differential arc length, you can either use this one or this one to represent it. Depends on the equation. So we use this formula. We found the surface area of this ring right here. So in this case, dy dx is actually easy to find. So we actually found dy dx. And it's revolved about this x-axis. So take the point on the curve and revolve about this x-axis. The circumference of this circle is 2 pi y. And then here's ds over here, the differential arc length. Notice that I don't put any upper and lower limit here because at this step, it's not clear I'm integrated with respect to x or y. So don't put an upper or lower limit right here. The next step over here, the ds, I express it in this form. So now I put the dx over here. X go from -1 to 1. Now I put down the upper and lower limit over here. And then you just need to do the algebra over here and then find this integral. So we stop it over here. So this ring here has surface area to be 8 pi. Let's do one more example. We have y equal to x squared. Now the curve of this, so this is a hyperbola. So here's is the point 1, 1, and then another point here, 2, 4. And we have this arc over here. And we're going to revolve this arc about this y-axis. Now we get a surface of revolution. I'll highlight this. So this is the surface of revolution. Now, how can I find this surface area here? So the surface area, let's call that S. That's equal to the integral of, can someone tell me what's that integral? You pick a point on the curve, right? So this is x comma y. And you rotate this point about this y-axis. So you're going to chase out this circle here. The radius for this circle here corresponds to the x. So that is going to be 2 pi x. And the differential arc length ds over here, 2 pi and x. For the ds over here, I can decide which one to use. If I look at this, it's actually easier to find dy dx. So from this, dy dx is actually easier. Okay, so that is going to be equal to x. Now we're going to express this ds over here by using this 1 plus dy dx square, right? Because dy dx we found it over here, right? So now I can put down the upper and lower limit here. So x over here go from 1 and end it at 2. So x go from 1 to 2. 1 here to 2. So I set up the integral over here. Now this one, we can take the 2 pi in front of the integral. That's just a constant multiple. And then we have this x over here, square root of 1 plus dy dx. We just found that it is 2x. So square that, we get 4x squared. And then dx. X go from 1 to 2, right? Okay. Now, how do I find this integral? What kind of method? What kind of integration method to do?
U-sub?
Yes, U-sub, you got it. Okay. So we're going to use U-sub because so we want this to be a single variable. So U equal to 1 plus 4x squared. Then du is going to be 8x dx. And you see that it's going to match with this x over here, dx over here, right? So when you see this is 1 degree higher than that, and when you differentiate this, you get something related to this x over here, right? Then you know you make the right choice. Okay, so match with that. So match with this. All right, so now after that, so we have the 2 pi outside. Then this is going to become u. So u to the 1/2 power because square root is the same as the 1/2 power. Now x dx over here, x dx is du over 8. Now over 8, you can put it in front, but let's just leave it over here. Now, once I did the U-sub, this is integration with respect to u. Okay, so I need to find the corresponding upper and lower limit of u. X goes from 1 to 2, then what does u go from? When x equal to 1, remember u is 1 plus 4x squared, right? So that's equal to 5. When x equal to 2, u is equal to 17. So the lower limit for u here is 5. Upper limit is 17. So don't forget to change the upper and lower limit once this is an integration with respect to u. Don't forget. Now over here, this is going to be 2 pi over 8. So that is pi over 4. Now anti-derivative u to the 1/2 power, it is u to the 3/2 times the reciprocal, so 2 over 3. And we found that u go from 5 to 17. So over here, if you simplify that, okay, that will become pi over 6. And inside here, you will have 17 to the 3/2 power, subtract 5 to the 3/2 power, and that will be the exact answer over here. So now this is one way to do it. Okay, some of you might wonder, what happens if I, instead of using this to express for the ds over here, the differential arc length, what about I use the other expression, right? So let's do it together. I'm going to do another solution, solution 2. The reason you can do this 2 different ways is because of the orientation of the curve. You see, y equal to x squared looks like this, right? And so look like that. And the curve that we have is like from here to here. So this is the arc that we have. You can slice it this way, right? But you can also slice it this way. You can slice it 2 different ways. So the ds here, you can express that either, the 2 different ways both work. Okay, so remember the ds. Okay, remember our ds. There are 2 different ways. One is if we put the dx outside, and the other one you can put dy outside. Okay, this is 1 plus, this one will be dy dx squared. This one over here will be 1 plus the square of dx dy. Okay, now because this arc can slice it this way and this way, both of them will work. So let's use this one. Okay, we already used this in the first solution. Let's use this one. So the surface area S, that's equal to the integral, it's the same, is 2 pi x. 2 pi x. Yeah, remember, that's common. So this is S over here. That's the radius of the circle. And then ds. Now for the ds here, I'm going to use this second expression over here. So we have 2 pi, and then so the second expression over here will have dy outside, and then we have 1 plus dx dy squared. Now because this is an integration with respect to y, I want everything in terms of y. So the s over here, I want it to be in terms of y. That's the integration of y. So we have y equal to x squared. And notice this arc here is at the first quadrant. If I solve for x, x will be positive. So x is positive square root of y because x is positive at the first quadrant. So this will be square root of y. Now we can put the upper and lower limit over here for the integral. The y here go from where to where? Y go from 1 to 4, right? So 1 here to 4 over here. So put down the upper and lower limit. Now let's take the 2 pi outside. This integral of square root of y, square root of 1 plus dx dy. Okay, let's find dx dy. Dx dy over here, it is going to be 1 over 2 square root of y. We did that many times, so we kind of remember this already, okay? Now when I square that, that is going to be 1 over 4y. So now we put this back. So this, we put it over here. So it's 1 over 4y, now here dy. Now you can multiply this in, right? They distribute. Okay. Oh, don't forget the upper and lower limit. It's from 1 to 4. Then this becomes 2 pi integral, and it is the square root of, you're going to get y plus 1 over 4 over here, and then this is dy. Y go from 1 to 4. Okay, if you do this integral by hand, what kind of method that you use to find this integral?
I think use up then.
Use up, you got it, okay? Okay, so we use up. So want this whole expression inside to be u. Okay, so we use up. U is equal to y plus 1 over 4. And so du is going to be just dy. Now you need to find the corresponding upper and lower limit for u. So when y equal to 1, u is going to be 1 and 1/4. Okay, let's write that in improper fraction. So it's 5 over 4. When y equal to the upper limit 4, u is going to be 4 and 1/4. In improper fraction is going to be 70 over 4. Okay. Okay, now after that, so this is going to be 2 pi, this integral. This is u, and the square root means it's to the 1/2 power. Dy is the same as du in this case. So that's du. And u here go from 5 over 4 to 17 over 4. So we change the upper and lower limit over here. So this is a simple integral, right? It's not too bad. So this is going to be 2 pi. Antideuty of u to the 1/2 power is going to be u to the 3/2 power times 2 over 3. U go from 5 over 4 to 17 over 4. So this is going to be, simplify this, is 4 over 3 pi times, well, now we substitute, right? Times 17 over 4, which is to the 3/2 power, minus 5 over 4 to the 3/2 power. And when you simplify this, it should be the same as the other one, which is the same as pi over 6, 17 to the 3/2 power, minus 5 to the 3/2 power over here. It's the same answer. So you see this in this problem, I show you how you can actually do it in 2 different ways. Depends on how the art is orientated. Now that's the end of our lesson, section 8.2.